Okay, this next short video about linear equations, we're going to focus on solving linear equations and solving systems of linear equations. Let's remember, what's a linear function? A linear function is one that if you sum together the inputs, it's equal to the sum of the outputs. Or if you multiply the input times a constant, it's equal to the constant times the function evaluated at that input. So we talked about a simple equation, y equals m times x, as being an example of a linear function. This is only a one-dimensional function, so it's pretty easy to solve. So if you give me y and say what's x, well, I can just write m inverse times y equals x. And what do I mean by inverse? I just mean 1 over m times y. That's easy to do. But what if we have a more complicated example? Okay, here's a more complicated example where we have two equations and two unknowns, x1 and x2, and I've gone ahead and just plugged in for an example of what y1 and y2 might equal. We can actually solve this set in general for any y1 and y2, but I want to do the concrete case first, and then we'll come back to see the solution for any y1 and any y2, and then we'll actually do it for any set of coefficients for the x variables next. Okay, so we can't easily read off the value of x1 or x2 off of the first equation, nor from the second equation, because they are simultaneously in operation. So you probably have learned lots of tricks to do this quickly, lots of different ways of solving these kinds of systems of equations. We're going to learn in general about these kind of equations representing them as matrices, thinking about the inverse of matrices and vectors and arrays and all that kind of stuff, which is sort of the shorthand notation for solving equations like this. In this particular case, let's just solve it to get what the answer is, and then we'll come back to think about it in a more abstract sense. So what if I take the first equation and add it to the second equation? If the first equation is true and the second equation is true, their sum is also a true equation. So what do we get from that? We would get 6 equals 4x1, and the x2's cancel, so there is no x2. And then we can go ahead and solve that equation to say that x1 is equal to 2/3. Did I get that right? I did not. 3/2. Aha! Okay, now we have the solution for x1. And now we can go back to either one of these equations and plug in this to find x2 from it. Let's do it in the first one first to see how that works. Plug it in for x2. So 2 equals x1, which is now 3/2 minus x2. So I'll move 3/2 to the other side. This is 4/2 minus 3/2 is 1/2 equals minus x2, or minus 1/2 equals plus x2. Great. That's what happened if I plugged it into the first equation, and now I'm done. I needed two equations, one for each of the unknowns. The first, when I add both of these equations together, they both count as one, and then I can go back and use either of the equations to find the other one. Would I get the same answer if I plug in here? Let's just check it. What's 4 equals 3x1, but x1, remember we found was 3/2. So 3 times x1 is 9/2 plus x2. Okay, 4 is 8/2. Minus 9/2 is minus 1/2 equals x2. Same answer from both. Check. But what if we didn't actually know what y1 and y2 were, but those were just some arbitrary things that we were going to find out later? Like, we are interested in inverting this set of equations in general for something on this side based on the values that we would get for x1 and x2 for any values of y1 and y2. Can we do that? Sure. Let's erase those specific examples and see what happens. Well, we follow the same procedure. We add together these two equations, and what happens is that we get y1 plus y2 equals 4x1. There is no x2. Adding them together was the simple thing to do to make sure that we canceled out one of the two variables. Okay, so this, we don't know what this is in general for x1 and x2, but we can, for any y1 and y2, we get, this is the value for x1. Now how do we find x2? Well, we go back in and we plug it back in just like we would have before. So let's use the first equation because that's a little simpler. y1 equals y1 plus y2 over y4 minus x2. I've just plugged in for x1. And now we can simplify this. We have 1 minus 1/4 y1. So we have 3/4 y1 plus minus 1/4 y2 equals minus x2. But let's flip the signs. x2. So here's our solution for x1, and here's our solution for x2. This will be the solution for any y1 and y2 we want. If we had used nonlinear sets of equations rather than linear sets of equations, it would have been trickier because we would have had to do like quadratic equations and things to get the solution of this sort. But in this case, we get one form of the equations that works in general. What happens if we can't just add these two together? What kind of thing might we have to do? Well, suppose we had a 2 here instead of the original equation. We couldn't just add them together, but I certainly could multiply both sides of this equation by 1/2 before adding them together, and then it would cancel out. Or I could have indeed multiplied the second equation by 2 and then added them together to get it to cancel out. Or in general, even if there was some really complicated function of x1s and x2s, I could manipulate both sides of the equations to change things until they were simple enough to cancel out one of the unknowns or certain combinations of the unknowns even. That's what matrices make very easy for us. And so let's follow that to its utmost conclusion and use just arbitrary coefficients, could be anything we want, for each of the x's, and leave the y's undetermined as well, and let's just solve this set of equations. Can we do that? Sure we can. It's just a little bit more work. Can we do it in general? Yes, we can. We'll be a little bit careful at the end and come back and notice that something has to not vanish for this to really make sense. If one particular combination of the coefficients does vanish, makes things a little bit finicky. That will be a really interesting exception that we'll keep coming back to later. Okay, how can we make, let's suppose we want to cancel out the x1 part, or no, let's cancel out the x2 part the same way that we did before. How can I make this equation and this equation such that I can cancel out this time plus this? Well, I can multiply both sides of this equation by minus b times minus b. And I can multiply both sides of this equation times d. And remember, what we're doing right now, what we're about to do, is using one of our linear, we're going to use both of our linear function relationships, this one and this one, in order to take the next step. So we know that because we've made these functions explicit, but all we're doing is returning to these linearity assumptions. Okay? So what happens now? Let's distribute this out. So we get dy1 minus by2 equals ad times x1 plus bd times x2. And this one we get minus bc times x1 minus bd times x2. And I've both distributed those coefficients out and also done some rearrangement, which is using the associative and commutative properties of multiplication, which is where we're going to see that and soon we'll see some objects that don't do those things quite as simply. But that's for the next little video. Now let's see what we've got. Now we've got, hey, look, there's a plus BD x2 and there's a minus BD x2. So let's add these two together. And we get D minus B times, oops, can't do that. Why can't I do that? Because this is y1 and y2. Those are not the same variable. So we get dy1 minus by2. No cancellation on that side. Do we get any cancellation on the x ones? No, we don't. We get AD minus BC. This is a special, AD minus BC is something special, which we'll talk about in a second. It's called the determinant. And BD minus BD, x2, x2, 0. Those cancel out. Okay, so I'm almost there in my solution for y1. I just need to divide by this AD minus BC. And that's why I was saying it's special. If it was 0, I would not be able to take the step of dividing by it. But if it's not 0, then I can. So this solution from now on depends on the fact that AD minus BC is not equal to 0. Okay, if AD minus BC is equal to 0, then we can just move it over here. Cancel it out on this side. And that's our solution for x1. How do we find our solution for x2? Well, we have to go back and plug it back in. So we can plug it into either the first equation or the second equation, whichever we prefer. Let's plug it into the first equation. And remember, we multiplied by d. We don't have to keep that part, but we're just going to plug in for the x1 here. So we have y1 equals a times x1, which is this solution. So a times dy1 plus, minus by2 over AD minus BC. That's this first term, and then the second term is plus b times x2. We don't know what x2 is. That's what we want to solve for. So let's solve for it. Okay, this is a bit complicated, so we need to simplify, distribute, and simplify. Okay, all right, let's do AD minus BC here, divided by AD minus BC here. So let's just multiply by a fancy kind of 1 over there. What have we got over here? Now we've got the same denominator on both sides, so I can move this over, and I get an ADY1, ADY1, great, BCY1, ABY2. The y1 part cancels, the y2 part does not cancel, and we get slowing down to double check that because I'm thinking that should not have worked. Okay, I almost canceled out something that it shouldn't have, so I'm glad I slowed down to check. Okay, ADY1 over AD minus BC, ADY1 on that side. That part of it cancels. So we got minus BCY1 divided by AD minus BC. And what about this part? That part we still get. So plus ABY2 over AD minus BC, which is equal to BX2. And let's cancel out the B's. Everybody's got a B. Okay. So this plus this, and we can write this one in a little bit simpler form. Let's write it as minus CY1 plus AY2 over AD minus BC equals X2. So here's the solution for X1. Here's the solution for X2 for all equations of this general type.